Hello everyone and welcome back to Power Electronics Lectures. Let's get started for this lecture, which is about a single phase full wave rectifier with L load. And this is a series of lectures on controlled rectifiers. In last lecture we stopped at a single phase full wave rectifier with R load. So now we replace the load with the R load with inductive load. And we assume that this inductive load is a highly inductive load. What do you mean by a highly inductive load? Highly inductive load like induction machine, like the machines or the load that consume a huge current. And once the machine consumes a huge current, this means the output current will be constant, as if it's a current source. Once I tell you that this is a highly inductive load, this means this machine or this load will hold the current forever, as if we have a current source. So if you look at this current here on the output, you'll find it constant current, right? Because the output is a highly inductive load. Now let's see how this Thyristor circuit works with a highly inductive load. We agreed that at this point here, we send signal to Thyristor 1 and Thyristor 2 when the input is positive. So these two thyristors receive signal when the input voltage is positive, and these two thyristors receive their firing signal when the input voltage is negative, Thyristor 3 and Thyristor 4. So let's say, for example, you want to take this portion and this portion. So at this point here, alpha 2 must be sent to Thyristor 3 and 4, and alpha 1 must be sent to Thyristor 1 and 2. Now, same behavior. When the input is positive and there is firing angle sent to there is firing signal sent to the Thyristor 1 and 2, you will find that the Thyristor 1 and 2 is conducting, and the output voltage is equal to how much? Is equal to the input voltage at this point. At the zero crossing here, because the load is a highly inductive load, so there is current all the time. So this thyristor will never stop, okay? Will keep conducting until Thyristor 3 and Thyristor 4 receive their signals. So here, once Thyristor 3 and Thyristor 4 receive their signals, you'll find that the voltage across this point, this conducting, and the voltage across Thyristor 1 will be negative. So here, before Thyristor 3, Thyristor 4 are conducting, what happens? Yes, the voltage across the thyristors will be negative, but because there is current on the output, so Thyristor 1 and 2 will keep conducting. Once Thyristor 3 and Thyristor 4 receive their signals, you'll find that this is conducting, and the voltage across Thyristor 1 here will be negative, and then Thyristor 1 will be off. Similarly, Thyristor 2 will be off as well. So the voltage across these two thyristors will be negative at this point, and then the output voltage will be same, but this is taken from the negative portion and this is taken from the positive portion. This is the case. How about the input current? The input current, when Thyristor 1 and 2 are conducting, you will find that the input current is plus I out. When Thyristor 3 and 4 are conducting, you will find that the input current is minus I out, okay, and this is I out. Plus I out, minus I out, and this will be like a very distorted signal, a very distorted waveform with high harmonics, okay, with a high amount of harmonics. Now let's try to find the average voltage for this output, okay, the red area here or the green area. It will be same, either the red or the green. So if you try to find the average voltage for this one, so this starts at T1 and ends at T over 2 plus T1. So here we can say that V out is equal to how much? 2 over T integration from T1 to T over 2 plus T1 V maximum sine 2 pi T over T dt. Again, sine, integration for sine is how much? Minus cosine. So this will be minus cosine pi plus 2 pi T1 over T plus cosine 2 pi T1 over T. Okay, because this is one side is T over 2 and here without T over 2, and all of this will be multiplied by what? By V maximum over pi. Here let's do some simplification for this one. This one will be how much? V maximum over pi, and this will be how much? Cosine 2 pi T1 over T. Okay, because cosine pi plus something, it's a minus cosine, that's something. Okay, so this will be cosine 2 pi T1 over T plus cosine 2 pi T1 over T again. And finally, V out will be equal to how much? 2 times V maximum over pi times cosine alpha. This is the average voltage for a single phase full wave controlled rectifier with L load. The difference here is that we added this portion here. We add this portion. Why? Because we have a high inductive load, and this inductive load consumes current all the time. So the thyristor will keep conducting until we send another signal to the what? Until we send another signal to the other thyristors, Thyristor 3 and Thyristor 4. Now this is the case for three-phase for a single-phase half-wave rectifier. Now let's move and see how things working within a three-phase half-wave rectifier. So here we have a three-phase half-wave controlled rectifier with R load, but at this point we have a small firing angle. Okay, we have a small firing angle, which means we send a firing angle to the thyristors before the thyristor, let's say, or before the waveform hits the zero line. So we think that there is no problems at this moment. If you look at the waveforms here, let's say that here we have VA, VB, and VC, and here we have thyristor 1, thyristor 2, and thyristor 3. At this point, we send signal to thyristor 1. This is alpha 1. And at this point, we send signal to thyristor 2. And this is, let's say, alpha B. This is alpha A. And this is alpha B. Which means this is alpha that is synchronized with phase A. The blue one is alpha, which is synchronized with phase B. And the last one, alpha, that is synchronized with phase C. Okay, so this is alpha C. So here, let's first imagine that we have diodes instead of the thyristors. Let's say here we have diodes instead of thyristors. What happens if we have diode? If the voltage difference across the diode is positive, then the waveform that has the higher voltage will move and will be to the output. This is the reference point, so this is alpha A, and this is alpha B, and this is alpha C. Okay, at the crossing here. Now, we said in the past, if we have a diode, because VA here is greater than VC and VB, then VA will win and will move to the output. Then the output voltage will be this portion, right? But now we have a problem. We have a thyristor. Thyristor has no signal until this point. Okay, until this point. So yes, the voltage is positive, but the firing signal is still not there. Once thyristor 1 receives the firing signal, then it will be conducting and the output voltage will be this portion. Until this point, what happens? We expect that phase B is greater than phase C. That's correct. Phase B is greater than phase C. But phase B is not conducting. Why? Because thyristor 2 haven't received the signal yet. So thyristor 2 will be waiting, ready. The voltage across thyristor 2 is positive, but it will be conducting when it receives the signal. At this point, thyristor 2 receives the signal, and then it will take over from thyristor 1 and will conduct. And from here to here, thyristor 1 will keep conducting, and so on. Until this point. Again, until this point. At this point, we expect that thyristor 3 will take over, but thyristor 3 has no order, okay, has no signal. So thyristor 2 will keep conducting until thyristor 3 receives the order, receives the firing signal, and at this point it will take over from thyristor 2 and conducting, and so on. So you'll find that at this point here, from here to here, thyristor 1 is conducting, from here to here, thyristor 2 is conducting, and from here to here, thyristor 3 is conducting, as if it's shifted. If you try to find the voltage, for example, across thyristor 1, like this one, you'll find that the voltage here, when thyristor 1 is conducting, what happens? The voltage across the thyristor is 0. When thyristor 2 is conducting, so the voltage across thyristor 1 will be how much? It will be VAB. When thyristor 1 is conducting, so this voltage will be VA and this is VA, so the voltage is 0, right? When thyristor 2 is conducting, so this will be how much? This will be VB, right? So the voltage across thyristor 1 will be how much? VAB. Okay, this will be VAB, right? Now, when thyristor 3 is conducting, so this will be how much? VC. And the voltage across thyristor 1 will be how much? It will be VAC, and so on and so forth. Now, this is the case for a three-phase half-wave rectifier. Life is easy with half-wave rectifier because we just care about the positive half-wave. Okay, we don't care about the negative half-wave. Next lecture we'll talk about the full-wave rectifier, but now we just focus on the half-wave three-phase rectifier, controlled rectifier. Now let's try to find this portion here, the average voltage for this portion, for the output voltage, and see how we can do this. Now the easiest way, if you try to compare this one with the diode rectifier, it's simple. We can just move the axis here, and instead of obtaining the average voltage for the sine waveform, we can move the axis to 0 here and make this one a cosine waveform. And take the integration from here to here, from minus something to plus something, from minus t over 6 plus the firing angle to t over 6 plus the firing angle. So here we can say that V out, now we redefine V out, the output waveform. Instead of sine wave, now we make it as cosine wave, cosine 2 pi t over t capital, and time is defined from minus t over 6 plus delta t to t over 6 plus delta t, or t1, it's up to you. So the average is equal to how much? V out is equal to, for the full period, we have 3 waveforms, right? So this will be how much? 1 over t over 3, right? So it will be 3 over t integration from minus t over 6 plus delta t to t over 6 plus delta t. And this will be V maximum cosine 2 pi t over t dt. Now again, this is just integration. Integration for cosine is equal to how much? Sine. So this will be sine pi over 3 plus 2 pi delta t over t minus again sine for the other part, which is how much? Minus pi over 3 plus 2 pi delta t over t capital, and all this is multiplied by 3v maximum over 2 pi. Now let's recall some trigonometric functions, which is sine x minus sine y is equal to how much? 2 times sine x minus y over 2 times cosine x plus y over 2. So we can define x as this value and y as this value, right? And say this is sine x minus sine y. I multiply them together. So we can cancel pi over 3 and 2 pi delta over 2 and over t, and this will make simplification for our waveform. Now you can just stop here and say, okay, this is the out waveform. If you have numbers, you can get the same answer. So this V out is equal to how much? V out is 3V maximum over 2 pi times 2 times sine pi over 3 times cosine the other part, which is 2 pi delta t over t. Let's move and simplify again. So this will be V out is equal to how much? 3V maximum over pi times sine pi over 3. It will be how much? The root square of 3 over 2 times cosine 2 pi delta t over t. And finally, this is alpha. V out, the average, is equal to how much? 3 times the root square of 3 times V maximum over 2 pi times cosine alpha. And this is the average voltage for 3-phase half-wave controlled rectifier. Of course, this is for a small firing angle. If the firing angle is greater than this, then you will find that the waveform can hit the zero line and it will be different. Or let's see if we have a 3-phase half-wave rectifier with a firing angle of 45 degrees, for example. Now here we have a 3-phase half-wave rectifier, controlled rectifier again, with R load and a 45 degrees firing angle. Now look at this here. Now the firing angle became greater here, larger. So this is alpha A, which is, well, this is not alpha A, this is the signal that is sent, but alpha A is from this point to this point. And this is alpha B, so this signal is sent to thyristor 2, and this is from this point to this point, let's say. So this is alpha B, and this is alpha C. Okay, so this is the signal that's sent to thyristor 3, and from here to here it's alpha C. Okay, clear? Now, what happens? Again, if we have a diode, if the voltage VA is greater than VB and VC, then we expect that this voltage is taking over and it will be going to the output. Okay, so the output will be VA. Again, because we have no signal sent yet to thyristor 1, so thyristor 1 will be off until it receives the signal alpha A at this point. So it will be conducting at this point. Okay, so the output will be conducting until this point. Now what happens here? Now at this point, this is a very important point here. Now at this point, thyristor 1 is conducting, but suddenly it hits the zero line. And also when thyristor 1 or when VA hits the zero line, thyristor 2 haven't received the firing signal yet. Neither thyristor 1 is conducting nor thyristor 2 is conducting. Okay, so both thyristor 1 and 2 are not conducting, both are off, and at this point you'll find that here we have what we call natural commutation. What happens at this moment? All thyristors are not conducting and the load is R load, okay, resistive load. so the current will not be able to keep any thyristor conducting, so all thyristors will be off and the output voltage will be 0. Here the voltage, as you see here, it's how much? It's 0. And here also the voltage is 0. Why? Because here VA is 0. So hits the 0 line. Thyristor 1, the voltage applied on thyristor 1 is negative, and thyristor 2 haven't received the signal yet, so the voltage here will be 0. Now once thyristor 2 receives the signal, it will be conducting and no problems. The output will be the voltage VB. Because of course here the signal is delayed, like it takes longer time to reach to the thyristor, so the voltage VB hits the 0 line before the next thyristor receives the firing signal. So this will be off. All thyristors will be off. This behavior not because of any thyristor, okay, because the thyristor 2 VB hits the 0 line, thyristor 2 is off accordingly, and thyristor 3 haven't received the signal yet, so all thyristors are off. Okay, all thyristors are off. And once thyristor 3 receives the signal, it will be conducting, and once it's conducting, the output waveform, it will be how much? It will be VC, and then this will hit 0 line, and again it will be off. All thyristors will be off until the next thyristor receive the signal, the firing signal, and so on and so forth. Now the output current here, because the output load is a resistive load, so the output current will be how much? It will be similar in shape to the output voltage, and it would look like this. Okay, it looks like this. Thyristor 1 voltage here, for example, when thyristor is conducting, you'll find that the thyristor value, the voltage across the thyristor is equal to 0. So this, if we have a greater firing angle, again here you'll find, if we try to find the voltage, we'll take the time from here to here, and this will be 0. Okay, so let's try to find the average voltage for this one. So V out is equal to how much? V maximum cosine 2 pi t over t, and this will be until t over 4, and here minus t over 6 plus delta t. So the start of this waveform, no difference from the previous one, but because this will hit the 0 line at t over 4, because we agreed that at 90 degrees became 0, and the 0 line instead of 180 degrees became 90 degrees. So this will be from minus t over 6 plus delta t until t over 4. So we can say that the average V out is equal to how much? Again, here you have 3 portions, so it will be 3 over t integration from minus t over 6 plus delta t until how much? Until t over 4. And this will be for V maximum cosine 2 pi t over t dt. Similar thing, we have no difference here. The integration of cosine sine, so this will be sine pi over 2 minus sine minus pi over 3 plus 2 pi delta t over t, and all of this will be multiplied by 3v maximum over 2 pi, and here sine 90, sine pi over 2 is equal to how much? 1, so this will be 1 minus sine pi over 3, and here we can say that sine minus sine x minus sine minus x is equal to how much? Sine x. And we can simplify this one, so this V out is equal to how much? 3 V maximum over 2 pi times 1 plus sine pi over 3 minus 2 pi delta t over t. This is equal to how much? This is alpha. So this will be exactly same equation here, but with replacing this to alpha. So we can say the average voltage for this waveform is equal to how much? The average voltage is equal to 3V maximum over 2 pi times 1 plus sine pi over 3 minus alpha. And this is the average waveform, okay, the average waveform for 3-phase half wave controlled rectifier with R load when the firing angle like is great enough until the waveform hits the zero line. Of course, now we are expert in bringing the average just to make integration for the waveform and we obtain the average voltage, right? Now just imagine if we have the same rectifier, 3-phase half-wave rectifier, okay, controlled rectifier of course, with L load, with inductive load. If we have inductive load, this means that the output current is continuous and thyristor will keep conducting, okay, the thyristor will keep conducting. If we have inductive load with a small firing angle, nothing happens, okay. This will be exactly same as R load, because in all cases this will not hit the zero line. This will never reach to the zero line. So we will not notice the difference. We are not noticing the difference at this point. So you'll find that the waveform is exactly same as a 3-wave half-wave rectifier with R load. Why? Because this point is still positive and the thyristor is conducting, no problems. And before this thyristor reach to the zero line, then the next thyristor will conduct and the output voltage will be similar to the previous one, no difference. But the problem here happens if this waveform VA, for example, hits the zero line before the next signal sent to the VB, sent to the second thyristor, to thyristor 2. Now let's have a look at when we have signal sent to thyristor 2, but after the waveform hits the zero line. What happens? Now look at this. Here we agreed that this is alpha 1, alpha A, okay, the signal that's sent to thyristor 1, and this is alpha B, the signal that is sent to thyristor 2, and here we have alpha C, the signal that is sent to thyristor 3. So at this point you'll find that what thyristor 3 is on. At this point thyristor 2 is on, and here thyristor 1 is on, is conducting. Now again the voltage is positive here, okay, the voltage is positive, and at this point we have thyristor 1 is conducting, so of course the voltage on the output will be exactly same as the voltage on what? As the voltage on thyristor, the voltage on VA, so this will be conducting. Now here is the problem. At this point the voltage across thyristor 1 is 0 and negative, but thyristor 1 will keep conducting. Thyristor 1 will keep conducting. Why? Because the load is inductive load, and if there is no any signal sent to thyristor 2, so thyristor 1 will keep conducting even if the voltage across this thyristor is negative. So it will keep conducting because there is current is flowing inside the thyristor, and then this will keep conducting until the next thyristor, until thyristor 2 receives the signal. Once thyristor 2 receives the signal, you'll find that VB will take over and goes to the output. And here is VB. At this point, we have the same problem here. Look at this here. We have the same problem, right? But because the voltage is negative and there is no signal sent to thyristor 3, this will keep conducting until thyristor 3 receives its firing signal. Once thyristor 3 receives its firing signal, then thyristor 3 will conduct at this moment, and then VC will take over and go to the output. So this is VC, this is coming to the output. Here, of course, the current, if you look at the current here, because we have inductive load, okay, L load, so you'll find that the current is continuous all the time, and this will make sure that any thyristor keeps conducting if there is no any other signals into the next thyristor. I hope that you enjoyed this lecture, and I'll see you next time.